Okay. All of a sudden I have a tickle in my throat. Oh well, I'll work through it. Okay, so I was looking at kind of what I wanted to cover this week, obviously, and I don't think we're going to finish exactly all the things. I don't think we'll get to transformations today. So what I was thinking we could do is if I made a video on transformations and you watch that instead of doing a lab, because I don't have any lab material. There is some stuff that we can do for section 1.8 and maybe 1.9, but we haven't gotten there yet. And we won't this week. So maybe I'll just leave that until next week. So my proposal is that I post a video on just transformations and you watch it instead of a lab tomorrow, which means you'll sort of have free time, sort of not. Kind of nice, kind of not. So instead of a lab tomorrow, I really thought we'd get through it, but it's not looking like it today. I will post a video for you to watch on your own time. Okay, so that's instead of a lab. You still have to do stuff. You still have to watch the video, but I don't have any lab material. So I'll post a video for you to watch on your own time. I do not have a lab for us this week. Right, I'm putting it off until next week once we've seen some of those concepts. So a little bit confusing. If you need me to clarify, let me know. But otherwise, the deal is I'll post a video. I'll try to keep it in the 50-minute window. So if you wanted to use your lab time to watch it, then you could. If you don't want to do that, it's still going to be about 50 minutes long. So you can watch it whenever you want before next class. Okay. Be sure to watch the video sometime before next class. So for the lab, I don't have a lab because we're kind of behind for where I wanted to be this week. And so I was hoping to do kind of section 1.8 a little bit in class and then do the lab portion of it because there's actually some lab stuff that we could do. But instead, I want to finish this week and then I'll move that. We'll do that lab next week. So you guys have been riddled with labs already, so we're okay. We're still okay. So I'm just going to use that time to finish this week because it's all theory. I don't know what to do for the lab. Yeah, so make sure that you're okay with that and you know what's going on. Okay, so as a little bit of review, and also to introduce kind of the new section. And so 1.6 is on discrete random variables. We already talked about discrete random variables last day. So I'm going to do a quick recap of what they are because that's going to be important, of course. And then we'll talk a little bit more about discrete random variables before we head into continuous random variables. So discrete random variables bring this closer. Usually my classes, I can just kind of talk and freehand it. Not for this class, yikes. So I need my notes handy. Okay, so the example that we used last day, right? So the example we saw last day introduce the ideas, so two main ideas of the PMF, the probability mass function, which is the probability of each discrete event, right? Because we have a discrete random variable. And then we talked about the cumulative distribution function, which is really just what's the probability of being up to and including some point, right? And eventually, once we've seen all the possible outcomes, then of course that total has to be 1. We've seen that for a very common continuous distribution even, right? The normal distribution is a continuous distribution. And we've even seen that we can find probabilities by finding areas under the curve. So what we're talking about isn't new. It's just how we're talking about it is new, right? And so that feels weird, probably. Okay, so the example we saw last day introduced the PMF, right? The probability mass function. I'll define it here again. Probability mass function. And CDFs, which is the cumulative. So it's right there in the word. Cumulative is up to and including some point. Distribution function. The example we saw last day introduced the PMF and CDF for a discrete random variable, RV. So just as a little recap, we defined the CDF. We defined the CDF as Fx, so capital F is going to be used to denote the CDF, which means it's the probability up to and including some point of the random variable x at some point x, is the probability that x is less than or equal to some point x, right? If we jump ahead and think about the continuous distribution, well, that would be the area under the curve to the left of some point x, right, for a normal distribution. That's the case for any distribution, but we're familiar with the normal distribution, so that's why I like to go there. So x, right, this lowercase x, it's hard to tell because I haven't typed these out, obviously, I'm just writing them, but this is a capital X and this is a lowercase x, and x is just a placeholder for whatever outcome the variable x can take on. Note that x is an ordinary variable, right? It's just a placeholder and is used to refer, to a value x the random variable can take on. So some outcome of x. We also saw last day that the CDF, it doesn't need to be continuous. In fact, if it's discontinuous or if it has kind of a stepwise situation, then we have a discrete random variable. That's why we call it a discrete random variable. So what we saw was that fx of x need not, that's a weird way to say it, but that's okay, need not be a continuous function. But it is always right continuous, meaning that, and I'll write it down, but as we approach some point x from the right, then the limit there has to be the same as the function at that point, right? So if we've got this stepwise here and I approach it and I've got the full dot up on top, then the limit as I approach x from the right is going to equal the function, whereas here we had an open dot down here. So if I approach it from the left, then the function's up here, but the limit is down here. So that would be not continuous from the left, right? But it has to be continuous from the right, and that's the only condition. But it is always right continuous. So that is, yeah, exactly. Like that last example we saw. So that means that the limit, and I'm going to mix it up. Sometimes I'll use the notation that they use in the textbook, which is a little bit foreign to me. That's not how I'm used to seeing it. So I'll show you both ways. And then we'll get more comfortable with these different notations, right? So the limit as x kind of comes down on x naught is of fx of x should be fx of x naught. Or if you prefer, what's this saying? Well, it's saying that the limit as x approaches x naught from the right, so we use this kind of down arrow to show that it's coming down on some point, or an up arrow to show that it's approaching this point from kind of down under. I actually prefer the pluses and minuses because then I can read it as the limit as x approaches x naught from the right. I don't know, stuck in my old ways, I guess, of fx of x is going to be, again, fx of x naught, right? Just depending on which notation you prefer, doesn't matter. And we should be flexible enough to be able to read both, right? Or convert it to the one that you like. That's good too. Okay, so there were some properties. Now, these are not unfamiliar to us, but it's useful to kind of outline them once more. Things like the total area under the curve is 1. If you go to negative infinity, the area to the left of negative infinity should be 0, for example, right? And stuff like that. And so for a recap of the properties of fx of x. First thing is that it's a non-decreasing function, meaning it's not increasing necessarily. You could have, so you've got this kind of increasing situation, and then maybe you've got this plateau for a little section. That's allowed, as long as it's not decreasing at any point. Fx of x, remember, so it helps to remember what fx of x is. It's the cumulative distribution function. So saying that it can't be decreasing, that makes sense, right? Because we're adding up the probabilities up to and including that point, right? And so if nothing happened between the previous point and the new point you're interested in, well, then the probability, the sum of all the probabilities below it would be the same, right? So that's why it's non-decreasing. In fact, Remember, this is the CDF, the cumulative distribution function. Fx of x is a non-decreasing function. Okay. I just want to clarify here that as x increases, the total, or maybe I should say the cumulative probability less than x can't decrease, right? It can only only increase. It can only stay the same or increase. Okay. So what that means in terms of kind of notation is that for any A and B, A and B with A less than B, then we can say that the function, the cumulative distribution function of A must be less than or equal to Fx of B, right? It can be for any function, but especially if you think about a normal distribution, which, you know, we're still talking about discrete random variables, but the normal distribution is continuous and it's one that we've seen before. So I find it helpful to visualize. So if I have some point A and some point B, right? Maybe I should use a different color here. Maybe not that one. Then this area would be Fx of A, but this area, which includes that green area, which I'll show like this, must be Fx of B, right? So establishing that A is less than B on some number line, then the cumulative distribution function here to A must be less than. It could be equal to B if B is at A, or maybe something, or maybe nothing happened between A and B if the shape was something else, right? But the idea stays the same regardless of if we have a discrete distribution or a continuous distribution. So it just helps to see it with something that we know and love. And maybe, just maybe, there. All I wanted to do was write it the same way that I did the orange one, Fx of A. Another property that we said already, I think, can't remember, maybe not actually, maybe we didn't get to this one, but the cumulative distribution function at -infinity, thinking about, okay, well, I know how the normal distribution behaves. So if I'm out here at -infinity, the area to the left of that must be what, 0, right? And so that's the same as saying that the limit as x goes to -infinity of fx of x, well, that must be 0. Right? Same thing with positive infinity. If I've covered all possible outcomes, then the probability of being less than one of those things is, or all of those things is 1. So fx of infinity is the limit as x goes to infinity of fx of x, which must be 1. And then finally, we said fx of x is right continuous. Which we said was the limit as x approaches a from the right of f of x has to be the function, right, in order to be right continuous. Okay. Good. So even if we have a discrete function, or especially if we have a discrete function, but also for continuous functions later, we can use the CDF, the cumulative distribution function, to calculate areas between two values, right? It doesn't always just have to be the area to the left. We know that because if you want to find the area between a z of negative 1.29 and a z of 0.47, you could do that, right? You'd find the area to the left of 0.47, and then you'd find the area to the left of, I can't remember what it was, negative 1.29 maybe, right? And then you would do what? You would chop that area off, right, to find the area that you're interested in. Same thing applies, but here we go with the notation. So we can use the CDF to calculate the probability of any set of values, including an interval, that x can take on. So if we think about an interval, let's say, so for a half open interval, meaning it's closed on one side but not the other. So for a half open interval, we note that if A is less than B, right, which is a pretty typical notation, right? A is going to come before B on a number line. Then we have some x must be less than or equal to B, which is the same as what? It's the same as the union of, okay, well, if x is less than or equal to B and A is less than B, well, then that's the same interval as from x being less than or equal to A, or x being between A and B. So what we do is we break up the interval into two sections and form a union. So we can say that this is the same as x being less than or equal to A, or, so a union, A is less than x, which is less than or equal to B. Okay. You can think of this in terms of a number line, right? If you have A and B, right, then x being less than or equal to B is going to be this region here. And I should do a big thick dot here. X is less than or equal to B. I could break that up. If I know that A is less than B, right, then I can take this X must be less than or equal to A. So then it could be this one here. Oops, sorry. X less than or equal to A. I can't remember what I said, but that's what I meant. And then if A is already taken here, then I could have an open dot at A to join them up, followed by a closed dot at B, right? So now this is the same as X is less than or equal to B, but also greater than A. Right, so we could, and this is the same method as we've seen before, right? Where I break it up into disjoint unions. There's no overlap here, right? So here, split into disjoint unions. Oops. Okay. So we can represent this interval X less than or equal to B as the union of two disjoint intervals. So what we can say then is, well, X being less than or equal to A happens with some probability. And so F of B, I'll write a note, but notice how now I've dropped that little subscript X because it's obvious that I'm only talking about the random variable X. There is no random variable Y, for example, right? And so because it's obvious, I can drop it, and I'll try, to keep things as simple as I can, but sometimes I'll reintroduce it just to emphasize, but you can drop it and that's okay. F of B is the probability that X is less than or equal to B. Okay, so then what can we do? Well, if I know that X less than or equal to B can be written as X less than or equal to A union X between A and B, then I can replace this probability with another probability, right? So then I can say that this is the same. And maybe what I'll do, because I'm going to end up focusing on this probability on the left-hand side, maybe what I'll do is I'll scoot this over here. And I'll use it as a go-between. I don't like to have equal signs all in a row like this, but you'll see what I'm doing in just a second here. So this is going to be the same as the probability that X is less than or equal to A. And then the disjoint union says that, okay, because there's no overlap here, I can actually just take the probability that X is less than or equal to A plus the probability that X is less than or equal to B, but greater than A. Okay. This I can rewrite as, of course, F of B, because I saw it here, right? That's where I started. But that means that this is F of A. Okay. So what I could do is I could ignore this F of B here because I'm calling it F of B here. Or I guess I could ignore this one, doesn't matter. But I could rearrange and solve for the probability that X is between A and B. We rearrange to find that the probability A less than X less than or equal to B must be F of B, oops, clean that up, minus F of A, right? I can subtract F of A from the left-hand side, be left with the probability that X is between A and B. Okay, Good. So that means that I could find, and that's exactly what we've used in the past, right? We haven't written it out like this, probably. That's crazy. But we do understand that we can find the probability of being in some interval by using the areas to the left, right, of the higher point minus the area to the left of the lower point. Okay. So here, I'm going to make a note. Notice we have dropped the subscript x and here I'll just do it like that because it's probably on the F that you're missing at the most, maybe. But I just want to make a note here. So we've dropped the subscript x since, and maybe I'll make it a bigger X here, since it is clear we are discussing the random variable x. Okay. We will reintroduce the subscripts once we need to differentiate between maybe a random variable x and a random variable y. We will reintroduce fx and px, etc., when we need to keep track of multiple random variables, which we will, multiple RVs, such as x and y. So in the discrete case, the probability at a specific point can be found. Okay, that's not the case for a continuous distribution. But what we're going to say is that the probability of a single value is going to be the amount of the discontinuity, so, or the size of the discontinuity. So the probability of a single value A is given by the size of the discontinuity. And maybe I should say in fx of x at A. So if I think about the probability that x equals some value A, what could I do if I think about here, right? If I know I can find the probability of x being in some interval, what if I close that interval? And we've seen that before, right? Especially when we start talking about limits and derivatives, we take values closer and closer and closer to the point, but not exactly at the point, right? And so we're going to do the exact same thing here. So the probability that x is equal to A is going to be the limit as x goes to A from the left. Why from the left? Because we want to capture that discontinuity, right? Because it's the size of the discontinuity of the probability that x is between some value x and A. It can be equal to A because A is the discontinuity, and it has to be right continuous, right? So it can happen at A, but X approaches A from the left, but it can never really get to A because there's that jump, right? Especially if you think back to that jump discontinuity. So what we're going to get is, well, I can rephrase this in terms of the PDFs like we just saw. Sorry, not the PDFs. We're not there yet. The CDFs. The limit as X approaches A from the left of fx of X minus fx of A. I feel like it should be the other way around. Okay. I guess if it's the size, it doesn't really matter. So let's keep going. So that's going to be, and maybe it'll kind of fall out. Maybe I had a typo somewhere. Fx of A minus the limit as X approaches A from the left of fx of A. No, that's just distributing the limit. No, I think these should be switched around. Anyways, I'll show you. It doesn't really matter. Fx of A minus fx A from, and they use a little negative in the textbook, which is really just approaching A. I'm okay with this, right? Because then it has to have the larger function on the first and then subtracting the smaller one. So I'll have to go back and backtrack here. But this is what I wanted, right? I wanted that cumulative distribution function at A, which is, if you think about the stepwise, it's up here, right? Versus minus down here, right, on the lower step, then this would be the probability of that happening. So the CDF of a random variable sometimes I forget to use the RV and I start writing it out and it's upsetting. The CDF of a random variable is equivalent to the probability function associated with it. Why is that? Well, it's because here we're talking about the probability that X equals A is some difference in the CDFs, right? So the CDF of a random variable is equivalent to the probability function associated with it. And I will follow it up with at least, this is true for discrete distributions, but at least if the events we are allowed to consider are limited to sets and intervals of values, right, which we saw earlier. Are limited to sets and intervals of values. Okay. So that's enough about discrete random variables for now. Obviously, they're going to come back up, but I also want to talk about continuous random variables, right? And so we've seen continuous random variables, but not in this way, right? The normal distribution is continuous, for example. I stole a different example, and it does have some leaps in it, which I'll point out, but the idea is pretty good. So that's why I stole it. Let's see here. So 1.7 is on continuous, and let me see. Nah, too long till a page break. Continuous random variables. So yeah, so the area under the curve really only applies to continuous distributions. So for discrete distributions, you would have to use kind of some summation, whereas for a continuous distribution, then we can integrate it, and then we can find the area under the curve. So good. So soon. And we're going to start with just baby integrals, right? And so nothing to be afraid of if you're not feeling 100% confident. I know I didn't really feel, I knew what to do in Calc 1 and 2, but it wasn't until Calc 3 and 4 where you get to do it all over again, basically, where it kind of solidified. So I'm not expecting you to be, integrating wizards or anything like that. But there are tools out there that you can use and you can kind of rely on. For us, this isn't a course in integration, but we will rely on integration to find areas under the curve, right? So if the CDF, well, if the CDF cumulative distribution function of a random variable is continuous, then we call it a continuous random variable. A continuous random variable. Okay. So what's interesting is usually I would just look at the variable, what types of outcomes can happen. And from there, you would be able to identify if it's discrete, if you're talking about things like age or kind of countable things. And then if I'm talking about speed or time or whatever, then I would consider a continuous variable, right? And so that would kind of put me in the right direction, but technically it's based off of the CDF, but it's going to be directly linked. So, but technically, you could turn any variable into a discrete variable, not necessarily a continuous variable. I'm just thinking, so any categorical variable, you could code them as 1, 2, 3, 4, 5. And I think that's what you mean. Maybe not. Sort of. Sold. Yeah, so there are actually very few variables that are truly continuous. but there are a lot of them that we consider continuous. So even something like time, we can actually only measure time down to a certain precision, right? Okay, yeah, nice. So sometimes we kind of get in our heads and we say, oh, well, I could only measure it to, you know, a millisecond, but time is always happening, right? And so our measuring device might not be able to get to it, but if we had a better device, we could measure time down to, you know, an infinite number of decimal places. Technically the same thing with age, but the way that we talk about age, you're either 1 year old, 2 years old, 3 years old, 4 years old, and that's what makes it discrete, even though it's continuous. Kind of confusing, but you could figure out how old someone is down to, I don't know, the second or more. But usually we say age, something like age where we're counting. So anything countable is going to be discrete. And then anything where you could dive deeper, well, then we're going to call it continuous. Okay. So if the CDF of a random variable is continuous, then we call it a continuous random variable. So if it is constant aside from discontinuities, right, then we can call it a discrete random variable, kind of referring to the previous section. So if it is constant aside from discontinuities, we call it a discrete random variable. So the example that I stole has to do with the colatitude, which is a measurement. So, you know, there's the longitude, there's the latitude of a location on the Earth, right? So longitude and latitude, I can never remember, but the latitude is the distance from the equator, right? And then longitude is kind of the other one. And so we're going to talk about the colatitude, and the reason is because we're going to be able to talk about the area starting from the North Pole. So the colatitude, I'll draw it, try to draw it, is going to be just kind of the opposite of the latitude. So from the North Pole down to the latitude, whereas the latitude goes from the equator up to the point, right? But and so what we're going to do is we're going to use it probably like vectors, but I'm really rusty on that stuff. So probably you're probably more brushed up on that than I am. We're just going to use it to show you. So I'm just going to give you the CDF, and then we're going to talk about what we call the PDF. So as an example of a continuous random variable, pick a point at random on a sphere. Okay. And note its colatitude. And note its colatitude. Okay, so what I'm going to do is I'm going to focus on just the 2D, so just the circle here, just to show you what I mean. There. Oh, should have let it straighten out here. Okay. Hey. How about that? like that. Okay, so here's the North Pole. And then what we're going to have is if we're talking about this point here, right, then this would be the latitude. And this would be the colatitude. Okay, that distance from the North Pole. Of course, on a sphere, we're actually dealing with this kind of, shouldn't it be perpendicular distance? I don't know. Perpendicular distance. I'm not really sure what you mean by that. I don't know. That's okay. It's okay. Oh, perpendicular distance from the equator. Oh, okay. So I think you know what you're talking about. The problem becomes that, okay, this is actually, how can I show that this thing is 3D? Because it's a dang sphere making a mess. So it could be anywhere. You're asking the tough questions. Well, it's just going to be, so the colatitude is an angle. So the latitude is an angle, right? And then the colatitude is just going to be, I guess, 90 degrees minus the latitude, or pi over 2 minus the latitude, depending on if you're working in radians or degrees, right? And so it's just going to be an angle. And I guess there's some dispute because American mathematicians decided to use phi, the Greek letter phi, whereas everyone else, I guess, uses theta to denote the colatitude. And so here, the colatitude is the angle down from the North Pole. For notation, Americans use phi, and everyone else uses theta. And we will call it x. So that's confusing in this case, I should say. Because it's going to be the random variable that we're interested in. Okay. So one of the problems is that we can't actually find the probability of exactly one point. Because if we think back to, okay, how do we find probabilities? They're areas under the curve. And so technically what I'm doing is I'm taking some interval and finding the area at a particular point. But the distance, right, the rise over run, the distance at a particular point is going to be 0, right? A minus A makes 0. So there's 0 area under the curve at every particular point. That's confusing because we do have area, right? At some point it lines up to some area, but only on intervals. Okay. And so we cannot say the probability that X is exactly 0 or pi over 2 or some other single value, that X is exactly 0 or pi over 2 or some other single value. But we can say that the probability of being within some angle X, so we can say that the probability, of being within some angle X of the North Pole is proportional to, and this is where I kind of, at first when I read it, I thought, oh yeah, okay, sure. And then I tried to figure out why, and I couldn't get there. So that's okay. We're just going to take it as a fact. I'm okay with that. That's usually how it is, right? So usually I'll give you the distribution or I'll give you the function, right? Just like in calculus, I'll give you the function and then I'll expect you to know what to do with that, right? And so it's not about developing these functions. That's for something way, way higher, right? So higher level than what we're doing right now. So that's not something I'm concerned with. I'll give you the function. So in this case, what we're saying is the probability of being within some angle X of the North Pole is proportional to the area within the polar cap down to colatitude X. I do want to highlight this will always, this will be given, right? Not something that you're expected to develop. Okay. So what does that mean? Well, it means that the probability of being within some angle X, right, the colatitude, is going to be proportional to the area within the polar cap down to some colatitude X, right? And so this is really cheesy, but I have a pretty fun globe. I should have grabbed it before. Right? But ta-da! Okay, so here I've got a globe. And so if I'm looking at the North Pole here, right, and I know it's kind of like this, but just to keep it straight up here, I've got my North Pole here. So then if I pick a point here, then the colatitude would be this angle, right? And so instead of saying, okay, the probability of being there in some angle, because I could have been anywhere on this circle and the colatitude would have been the same, right? And so now what I'm going to think about is I'm going to think about, okay, well, how much area did I take up of the entire sphere? Because that's going to be proportional to the probability of being within that angle, right? So not at that angle because we can't do that anymore, right? But we can find, okay, what's the probability of being within the North Pole and up here? Well, that area of the cap is very, very small, right? So that probability would be very, very small. What's the probability of being within the North Pole down to here? Well, it's going to be that cap relative to the rest of the sphere, right? And so, so that's what they're saying. Again, that's not something that you're expected to develop at all, but it is something that we're saying and that we're going to use. Because I find that that can be confusing, right? Was I supposed to come up with that? No, not at all. Right, so don't worry. But what this means, and again, something given, right? And so this means that, and this is also given, that the cumulative distribution function, the CDF, f of x, is either 0 if x is less than 0, right? That's just if you don't have an angle, a colatitude. It's going to be 1/2 times 1 minus the cos of x, and that's, again, just given. If what? If x is between 0 and pi. So 0 and pi, not including pi, because what happens when we reach pi? Remember, x, I'll put it down here. And maybe I'll put it in the center here, like that. X, remember, is the colatitude. So if we think about, okay, so now I'm here, and from 0 to halfway point, then I'm at pi over 2. And then once I've made it all the way down to pi, then I've covered the entire sphere, right? And there's nothing more to do, right? The probability of being at some point from 0 to pi is going to be 1. Right? And any point up to that point is going to be by the area of that polar cap, just kind of slowly melting down the sides here. Okay. And so we could visualize it, I guess, although I tried to draw it out and I didn't do a very good job. So that's when I remembered the globe that I have. Kind of fun to have a globe too. Wouldn't x be greater than pi? It is out of the domain, but x greater than or equal to pi. I think because when you're at pi, we have to include at pi, right? Because that's a possibility. And then anything beyond that, you could, I guess, in theory. So you make a good point because, well, so what we're thinking is, okay, could you even go beyond x equals pi? You could, but the total area doesn't decrease. It just stays at 1. So that's why it's constant. So it's kind of weird. Because I guess you could loop around, but as long as you've looped once, then you've covered the entire area. Yeah. Well, yeah, so it shouldn't decrease because the probability, because we're talking about the probability. So as soon as you've reached pi, then you've seen all the possible outcomes. And then it's just kind of weird to think about. I think we're just covering our bases. Same thing as here, x less than 0 can't happen, right? You could have a negative angle, but then I guess that would be kind of negative angles are going clockwise. But in this case, because it's the other way, it'd be going this way. So then it's 0. We're just not allowing it. But we're saying for x is less than 0, the cumulative distribution function is 0, right? Or the probability is 0. Once we pass pi, it's just always going to be 1. Yeah, but good call. And I think it's just because we're assuming that you're not going to swing up and then reverse the probabilities, because you can't take away from probabilities, the total probabilities. So once you've reached 1, you can't go back, because it's the sum of the probabilities up until that point. A little bit confusing. So what this would look like, though, is if you have, so what we're talking about here is if I have a sphere and I'm going to try to focus here. So if I go from this point, if we increase pi, it will still satisfy cos pi. I don't know. So I think the problem is the glitch here is that this is the cumulative distribution function. So once you've reached 1, you're just going to be at 1, because the sum of all the probabilities or all possible outcomes has to be 1. So you kind of max out. I think technically we could say just x equal to pi, but it's for any x less than or equal to pi. Or sorry, greater than or equal to pi. It's just going to be 1. It's just a fact. So here, if I think about something like that, right, then what we're saying is that, so here my x is somewhere between 0 and maybe pi over 2, right? Doesn't matter. But what we're saying is this cumulative distribution function here is the size of this cap. And then if we go to pi over 2, that's not pi over 2 usually, right? But if we're talking about the colatitude, then it is the colatitude of pi over 2. So then we're talking about the probability there must be 1/2, right? Because it's half of the sphere. The probability at x equals pi over 2 must be 1/2, since it is half of the sphere. Okay. Same thing here. If you go to 1, or sorry, to pi, then the probability of being somewhere in this range is 1. So then we're talking about, okay, what happens if you go beyond here? And I would argue that it can't happen, because then that would be the colatitude on this side, right? And we've already covered that in this range. So what we find is that we can map the CDF. We can visualize the CDF like this. So if I have fx of x, and I've got a cutoff point at 0.5 and 1.0, halfway mark, I've got pi over 2, and then I've got pi. What's going to happen is at 0.5 and pi over 2, I'm going to reach an inflection point here. So it's going to look like this. And it technically keeps going in either direction, even though we're only restricted to 0 to pi. Nothing else can really happen. So what we're going to say is that note that in this case, the CDF is continuous. Probably. Sorry, I was distracted by the sigmoid. I don't remember, but that doesn't matter. So here, this means that the probability of X taking on any one value is going to be 0. And that's always the case for continuous distributions. And so this means that the probability of X taking on any one value, like 0 or pi over 4, is 0. Okay. But of course, if we're talking about an interval, then there is some probability there. So, but of course, we have a non-zero probability of X lying within an interval. Which we said before, right? We said that the probability that X is between A and B for continuous distributions, it can include B, it doesn't have to include B. So here it's going to be the same as the probability that X is up to and including B. And I'll highlight the differences here. But then once we have this set up here, then we can rewrite it just as we saw before, which is the same as fx of B minus fx of A. Since this is continuous, right, we can define its derivative. Finally, something we like. Apparently, you guys are all mathy. And I have been doing stats for forever, so I'm rusty on the math part, but the stats part is fun. But so we'll take turns. But since fx of x is continuous, we can define its derivative. And we're going to define it as a lowercase fx of x, which is the derivative of fx of x, which is known as the probability density function. Which is known as the probability density function. I think I let it slip earlier. I didn't mean to. The PDF. The PDF, the probability density function, is the continuous version of the PMF. Okay, and I'll say for the random variable. It's the continuous version of the PMF. I just find that it's helpful to keep track of those. And I see I'm running out of time, but I just have a little bit that I want to say here with the PDF. And so what we're going to say is the probability then, the probability that X is between some variable or some value A and B. Well, if that's fx of b minus fx of a, like we just said, that looks like something else. That looks like the integral from a to b of fx of x dx, right? So usually we would start here and I would give you the probability density function and ask you to find the probability of being between two values A and B. So then you would integrate that function, and then that's how you're going to solve the area between 2 points, A and B. So in this case, I know I don't have time to elaborate, so I'll just write it down so that we have it. In this case, fx of x, if you take the derivative of the CDF that we had before, it's going to be 1/2 sine of x for x between 0 and pi. And the derivative of a constant is 0. So it's 0 otherwise. Okay. And here I'll just show you, which looks like, and I'm trying to keep it on the same page here, which looks like fx of x maxes out at 0.5, and it goes from pi over 2 to pi. This is x, and it kind of move my pi over like that. Like that. Okay. I'm all out of time, and just like I thought, I didn't get to do transformations. So what I'll do is I'll make a video for you guys to watch on your own time instead of a lab, okay, this week. All right, so that means that I won't see you until Tuesday. So I hope that you have a good long weekend. And if you have any questions, and remember, Monday's a holiday, don't forget. So if you have any questions, let me know. Otherwise, have a great weekend.